Okay, so for tutorial 10, modeling of a catalytic chemical reactor, your task as a design engineer in a chemical company is to model a fixed bed reactor packed with the company proprietary catalyst of spherical shape. The catalyst is specific for the removal of a toxic gas at a very low concentration in air, and the information provided from the catalytic division is that the reaction is first order with respect to the toxic gas concentration. The reaction rate has units of moles of toxic gas removed per mass of catalyst per time. The reaction is new and the rate constant is non-standard, that is, its value does not fall into the range of values known to your group of design engineers. Your first attempt, therefore, is to model the reactor in the simplest possible way so that you can develop some intuition about the system before any further modeling attempts are made to describe it exactly. So for problem A, for simplicity, assume that there is no appreciable diffusion inside the catalyst and that diffusion along the axial direction is negligible. Okay, an isothermal condition is also assumed that this assumption is known to be invalid when the reaction is very fast and the heat of reaction is high. So the coordinate z is measured from the entrance of the packed bed. Okay, and perform the mass balance around a thin shell at the position z with the shell thickness of delta z, and show that the limit of the shell thickness approaching zero, the following relation is obtained. So where mu O or mu zero is the superficial velocity, C is the toxic gas concentration, epsilon is the bed porosity, rho P is the catalyst density, and Kc is the chemical reaction rate per unit catalyst mass. Okay, so we are asked to do a simple mass balance. Oops, sorry. Okay, so of course we will have our rate of mass in. So we will have our rate of mass in, okay, minus the rate of the mass out plus the rate of the gas consumed. So the rate of your mass in is given by the velocity multiplied by the area and the concentration. Z minus UOAC, that's Z plus delta Z minus the rate of gas consumed, okay, which is K C1 minus epsilon, okay, rho P A delta Z equals to 0. So we divide everything by A delta Z and we arrange it and we take the limit of it as well. Okay, so after dividing and rearranging, we should get plus delta Z minus UOC at Z over delta Z equals to, so when this is moved over it's positive, but we have switch places of this, so this one will be negative K C 1 minus epsilon rho P. Okay, so we take the limit of this as delta Z approaches 0, okay, which will give us d UOC over dz equals to negative Kc 1 minus epsilon rho P. Okay, so because this velocity is not a function of z, so we can take it out. So we should get dc over dz equals to negative 1 minus epsilon rho P and Kc. Okay, so the next part is now For problem B, okay, let's look at problem B and C together. This is a pretty short one. So show that this lump parameter model has the solution of this, where CO denotes the entrance condition. Okay, and the solution given in part B yields the distribution of the toxic gas. Okay, and concentration along the length of the reactor. Note that the exponential decline of the concentration. Okay, so show that the toxic concentration at the exit, which is required to calculate the conversion, is this. Okay. Now, let's move this one further. Now, looking at problem B, so looking at problem B, so from A, what's the mouse? Okay, so for B, now from A, we obtain that dC dz is equal to negative 1 minus epsilon rho p k divided by the superficial velocity by the concentration. So in here we will integrate this. Okay, so we will put c over and the z over, meaning to say we have dc over c equals to negative 1 minus epsilon rho p k mu o and dz. So we integrate this, and this one will integrate it like that. Okay, so over here we should get ln c, okay, and over here we should get negative 1 minus epsilon rho p k u o z plus alpha, your constant. Okay, so if we rearrange, okay, so we get this to be exponential of this 1 minus epsilon rho p k z over mu o plus alpha. Okay, so the exponential of this plus this gives you rho p k z over mu o multiplied by exponential of alpha. So we shall take this one to be a. Therefore, it gives us a exponential of the above following over here. Okay. Now, given that the initial condition at z equals to 0, okay, c equals to CO. Okay, so at z equals to 0, okay, we know that c equals to CO. Therefore, when z equals to 0 over here, we get that c is equal to a, right? Because exponential of 0 is 1. So c is equal to a. Therefore, CO, again, c is equal to a, and therefore CO is equal to a. Okay, therefore, I'll write it over here. So we have that C equals to CO exponential of Okay, so we bring CO over and take ln on both sides. Take the log of the both side over here. So we should get ln C over CO equals to, so if we take the ln of the exponent, it becomes rho pk over velocity multiplied by z. Okay. Now for part C, show that the concentration at the exit is given as such. We should look at our question again. So the solution given in part B yields the distribution of the toxic gas concentration along the length of the reactor, and note that the exponential decline of the concentration, and show that the toxic concentration results in this. All right. Therefore, from B we know that. Okay. So for part C, from B we know that we have found this equation over here, which is okay. So at Z equals to L, C equals to CL, right? So we substitute this and this one with L. This one substitute with L. This one we substitute with CL. Okay. So it's very simple, and we get over CO equals to negative L. Okay, so rearrange, we should get CL is equals to CO. Okay, and reversing it again. Okay, so that's for part C. Now let's look at part D. Okay, so in reactor design, the information normally provided is throughput and mass of catalyst. So if you multiply by the denominator and numerator of the bracket term in the last part by the cross-sectional area A, show that the exit concentration is this, where W is the mass of catalyst and F is the volumetric gas flow rate. Right. And for E, the dimensionless argument Wk over F is a key design parameter. To achieve a 95% conversion, where the conversion is defined as this, show that the non-dimensional group this must be equal to 3. This means that if the throughput is provided and the rate constant is known, the mass of catalyst required is simply calculated as W is equal to 3F over K. Okay. So we should go back to here. So for part D, okay, so I want to show the equation with the variable. Okay. Something thicker. Let's try this. All right. So CL is equals to CO exponent of this was from part C, right? Rho P KL over mu 0. Okay. And we multiply multiply it by we multiply it with A over here. Okay, so this was from equation 3, and we shall multiply it with A over A, which means we multiply it by 1. Okay, so we let F to be mu A, and W, which is the mass of the catalyst, to be 1 minus epsilon rho PLA, okay, which is this one, and this one to be your W, and this one to be your F. Therefore, we should get CO exponent of negative your W multiplied by your K. Okay, so WK over F. Okay, pretty simple, right? And then for part E, so in order to achieve a 95% conversion, okay, we are given this equation in which X is CO minus CL over CO, okay? So we want to set X to be equal to 0.95, correct? Okay, so over here, CO minus CL over CO is equals to 0.95. So CL, we will substitute with this equation, in which we will get CO minus CO exponent of negative W K over F divided by CO. So this is a factor. So this one becomes 1, this one is cancelled off, and this one is cancelled off. So 0.95. So we get 1 minus xp exponent of negative WK over F equals 0.95. Okay. So rearrange this. So bring this over. So exponent of negative WK over F is equal to 0.05. So we take the log, okay, of it, and we get WKF is to ln 0.05. Therefore, WKF is actually equal to 3, and W is, rearrange it, we get 3F over K. Okay. Now, moving on to the next problem. For part F, the elementary model 1 is of the lump parameter type, and its validity is questionable because of a number of assumptions posed. To check its validity, you wish to relax one of the assumptions and move one level up the hierarchy ladder. Suppose you relax the axial diffusion assumption, and hence show that the mass balance when diffusion is important becomes this. And since this is a second order ordinary differential equation, two boundary conditions must be required. Okay, two possible conditions after Danckwerts are such. Okay, so we are at F, right? So looking at problem F, so looking at F, okay, so in this case we will have to do the balance in which we consider the rate of the mass in and the rate of the in and out, as well as the rate of the diffusion in and out, as well as the rate of the gas consumed. So like previously in part A, the rate of the mass in is at C and Z, okay, minus OA C at Z plus delta Z, okay, plus, okay, the rate of diffusion is given by A epsilon J at C minus A epsilon J at C plus delta Z, okay, as well as the rate of the gas consumed plus, sorry, minus minus Kc 1 minus epsilon rho P A delta Z equals to 0. Okay, so we divide everything by A and delta Z, and we rearrange it as well as we take the limit of it. So we should get UOC at Z plus delta Z minus UOC Z, okay, divided by delta Z minus okay, so this one was supposed to be plus, okay, it's supposed to be plus, but because we rearranged this one, so over here we should have a negative here as well, okay, minus Kc 1 minus epsilon rho P A delta Z equals to 0. And then we take the limit as delta Z approaches 0 for both of this. Okay, and then we should get negative D of C divided by dz minus dej over dz. Sorry, this one is minus Kc or P. Oops, sorry, this one should not be here because we have divided it. It equals to 0. Then we take out the constant, okay? We take epsilon out because it's not a function of it, which gives us negative UO dc dz minus epsilon dj dz minus kc 1 minus epsilon p equals to 0. Okay, so we substitute j equals to negative d dc dz, okay, in which we should get negative UO dc dz minus epsilon d over dz, in which your j is actually negative d dc dz minus kc okay. So then we arrange the equation, we should get, so this one becomes positive, we should get d d d squared d. Okay, now, so that's for part F. Let's check out the next problem. So define the following dimensionless, non-dimensional variables, okay, and parameters, okay, and show that the resulting model equations are this, and at this condition we get this. Okay, so compare this model, okay, with so this model we call it as model 2, and compare it with model 1, okay, and show that the axial diffusion may be ignored when PE is larger than 1. So this can be accomplished by several ways: by decreasing the porosity epsilon, or by reducing the, or by increasing the velocity or the length. Okay, so get back here. So for part G, so G, okay, so we are given that y is equal to c over co. Therefore, c is equal to coy, and dc dy is co, right? And we are given that x is equal to z over l, right? Therefore, z is equals to lx. So, so dc dx is equals to L. Right? Therefore, from here we can simplify our dc dz to be, okay, so it is actually this multiplied by dx over dz x multiplied by dy dx. Okay, so dy is cancelled off here, dx is cancelled off here, so we get dc dz. So this is your CO, and this is your division of L. So we get CO L multiplied by dy dx. Okay, so of course d square c over dz squared is equal to d dz multiplied by dc dz, right? Therefore, it is so dz is L dx multiplied by dc dz is this. Okay, so when we take it out, we get CO over L squared multiplied by d square y over dx square. Okay, so we substitute this and this into the equation from the one that we solved in F. So substitute everything in, we should get, okay, I'm not gonna rewrite the equation from F, but I'll straight away put this in, CO over L, L square actually, and d square y dx square minus UO CO divided by L dy dx, okay, minus kc 1 minus epsilon rho P equals to 0. So we multiply by we multiply by L over COUO, okay, to get rid of the constants and make it more simpler. Okay, so after multiplying it, okay, we should get DE over UOL, sorry, and D square Y dx square minus dy k c over co L over UO and A over A divided by 1 minus epsilon rho P equals to 0. Okay, so this is your Y, right? As given, okay, and UOA as just now how we defined previously, this is your F, okay, in the previous section, and L, A, and this whole section is your W, okay, like previously. Okay, so we simplify this, and this one we shall take this one as 1 over PE. We take this one as 1 over PE. So meaning to say in the end we get 1 over PE d square y dx square minus dy dx minus k or wk over f y equals to 0. And we take this one as your n. Okay, make it easier. So this is actually 1 over PE d square y dx square minus dy dx minus ny equals to 0. So this is your model 2. So if we look at the boundary conditions, okay, so this one is your model 2. Okay. So if we look at the boundary conditions, in which at when z equals to 0, UO CO is equals to UO C at z equals to 0 minus d epsilon dc dz at z equals to 0. Okay, so this one we replace it with c over L again. Minus dE c over CO over L. Sorry. C over L. So this one, like we have found previously, this one is dy dx at x equals to 0, because now everything is it is a function of x over here. Okay, but this one is a function of c over here, so now we change it to x. Right, so we divide everything by UOCO. Okay, so this one we divide by UOCO, this one becomes 1 equals to this one we divide by UOCO, so we get C over, so U is cancelled, over CO at Z equals to 0 minus E U O L dy dx at x equals to 0. Okay, so over here, this one should be x also, x equals to 0. Okay, therefore, so C over CO again, this is y, so we get y at x equals to 0 minus, so this is your 1 over PE, okay, remember like previously, so d, oh god, this is D, okay, so this one is your 1 over PE, okay, dy dx at x equals to 0. Okay. Now, when z equals to L, your dc dz, when here z equals to L, dc dz is equals to 0. So in this case, CO divided by L dy dx is equals to dc over dz, right? So this one becomes 0 because this equals to this, which equals to 0. So when x equals to 1, when x is equals to 1, dy dx becomes 0. Okay, so model 1 is dy dx plus ny equals to 0. So when we compare these two models, model 1 and model 2, the previous one, it can be seen that the model 2 reduces to model 1 when PE is actually greater than 1. Okay? Right now, for part H. So to study the effect of the mass transfer inside the catalyst particle, we need to remove the assumption of no diffusion resistance inside the particle. This means that the mass balance within the particle must be linked with the external composition. To investigate this effect, we shall ignore the axial diffusion, which is usually small for packing made up of finely granulated solid, and the external film resistance surrounding the particle. Set up a thin spherical shell as a control volume inside the particle and show that the mass balance equation is this. So where Cp is the toxic gas concentration within the particle and dE is the effective diffusivity and is defined as Ficken-like. Okay, the Ficken-like relationship. So this one is very simple. So we would set up the shell balance. We will do a shell balance. Okay. So this one is your. So this is okay. This is how it looks like. This is the catalyst particle. So the diffusion goes outward. So okay, let's say you have a shell over here. You have a very thin shell over here. Okay, this one is your shell. So this shell distance, the distance between the shell is delta R. Okay, so in here, this part here, the inside here, maybe let's draw it larger. Maybe you can draw Again. Let's draw another one outside. Larger. Okay, simple. So the one in the red dot is your shell. Right now, okay, so the shell distance is delta R and the diffusion goes from inside to outside, so which is like this. Okay, so we have to consider the rate of the diffusion in at R and the rate of the diffusion out at R plus delta R, as well as the rate of the removal of the toxic gas. Okay, so the rate of the diffusion in at R is given by 4 pi. So this is a sphere, so 4 pi R squared J R area minus 4 pi R squared J at R plus delta R minus your K CP 4 pi R squared delta R rho P equals to 0. So this one is your rate of removal of the toxic gas. And we divide everything by 4 pi delta R. 4 pi delta R. And we rearrange it and take the limit of it as delta R approaches 0. Okay, we should get R squared J R plus delta R minus R squared J R over delta R KCP R squared rho P equals to 0. So again, we substitute J equals to negative dE dC P over dr. Okay. So over here we should get negative. Oops, sorry, this one we have negative here. Okay, so we should get negative d r squared j over dr first. Okay, minus k cp r squared rho p equals to 0. Okay, so substitute your j. Okay, and in which we should get negative d over dr Okay, so rearrange everything, we will get the final form as requested. So because this is R is a function of it, so we should keep this one inside dCp over dr minus k cp rho p equals to 0. Right. Okay. Now, so the final question, and next set up the mass balance around the thin element spanning the whole column. across the whole column cross section as in model 1, but this time the control volume will exclude the catalyst volume. This means that the material is lost to the various sinks made up by the particles. Show that the mass balance equation on this new control volume is this. Okay, so in this case, we'll do again mass balance. So we wrote down this one is H. Let's write this down first. This one was for H. Okay. I, last section. Okay, so we have your rate of mass in at Z, same thing, UOA, C at Z at Z minus UOA C at Z plus delta Z minus your rate of your gas consumed in the catalyst, which is given by 1 minus epsilon, okay, 3 over R JP A delta Z equals to 0. So we divide everything by A and delta Z, and we take the limit of it again. We get so we take the limit as delta Z approaches 0, and this one we should get this minus U O C Z plus 1 over E 3 over R JP equals to 0. Okay, so this one, after you take the limit, we should get negative D UOC over DZ minus equals to 0. So again, we substitute JP with negative DE dou CP and dou R. Okay, so this one gives us negative. So this one can be taken out. Okay, it's only a constant. Minus. So this one is negative DE dou CP over dou R equals to 0. Okay, so we arrange the equation and we get so this one is negative, negative, positive, and then bring it over so it becomes positive again. Put this in DE. Okay, so that's all for tutorial 10.